Yeah, today is the first lecture of whole course of linear algebra, and we will discuss today the vector space, what is vector space, and some example of vector space. First, we will discuss definition. What is vector space? Let V be a given non-empty set. We have taken a non-empty set because if we define functions, we will define a function from on V. So we have to take V as a non-empty set, okay, and F be any field. We have taken two objects. One is a set which is non-empty, and other is a field which is any field we can take. Okay. Now assume plus is a functions from V cross V to V, and dot is also a functions from F cross V to V are functions, and we will call both functions as operation. Okay, we will call this function as operation. Now then V plus dot is a vector space. Yeah. If yeah, this is only for notation of vector space. This thing is the only for notation of vector space. Nothing else. We will say V is a vector space with respect to the operation plus and dot, and we all and the vector space is always have a field. Okay, so V plus dot is a vector space if first condition V plus is abelian group. Abelian group. Okay, so first condition should be that V, and with respect to first operation which is plus, this set should forms an abelian group. What is abelian group? Now abelian group is a group which follows commutative properties. Okay, so first should be V is closed. First property should be V is closed under addition, and if we call this function as addition, it can be addition and any functions whatever we will define. Okay, and V is a closed under addition. V has associative properties. Associative property, that is for all x, y, z belongs to V, x plus y plus z is equal to x plus y plus z. If we add first two terms and then add last term, and if we add last two terms and add first term, both will be equal, then we say the associative property holds. Okay, now third property is V has identity element which should be unique. Okay, V has identity element, that is there exists, if we name that element 0 belongs to P, there exists 0 belong to P such that, otherwise we can take also X, there will be no problem for that. If we take X belongs to P, then for all y belongs to V, we should have x plus y equal to y. Then we say x is an identity element of V. We are checking when V is a abelian group, and this is the properties of abelian group, when a group will be abelian, and when we say a set and operations forms a abelian group. Okay. So if we take, and now we have an every element of V has inverse, that is for all x belongs to V, there exists to y belongs to V such that x plus y equal to identity element. Okay. Now we have as closed property, associativity, an identity element, and inverse. So it forms a group. And if we take commutative property, for all x y belongs to V, x plus y should be equal to y plus x. This is commutative properties. If a set with operation holds these 5 properties, then we say that set this is a abelian group. Okay. Now for to be a vector space, we need to check first a set with first operation is an abelian group or not. If not, we will say that the given set and the corresponding operations, that will not form a vector space. Okay. If V plus is abelian group, first condition. Second property should be for an abelian group of 1 dot x equal to x for all x belongs to B and 1 belongs to field. 1 is a multiplicative identity of the field. Okay, and x is belonging to V. This property should be called 1 dot x equal to x. And third property is, this is the second operation what we have written here. First operation is a plus, and second operation is a dot. So now we are dealing with the second operation, 1 dot x equal to x. Now a into this should be dot x plus y. A dot x plus y equal to a x plus ay for all x y belongs to V and a belongs to F. Okay, here the operation between a and x is the dot. I have not written here, but we should know that operation in a and x should be dot. Okay, now properties 4. What is the fourth properties? A plus b dot x should be equal to a dot x plus b dot x. Sorry, this should be x. Okay, so a plus b dot x equal to a dot x plus b dot x for all x y belongs to V and for all x belongs to V and AB will be in the field. So x belongs to V and A comma B belongs to field. Okay, and this uh, both property is called distributive properties. Distributive properties. Okay, and fifth property will be uh, a p x equal to a b x for all a b belongs to field and x belongs to a. Then we say, yeah, then we say v plus dot is a vector space. Okay, these are the properties of a vector space. Okay, now one should keep in mind that here A is a member of field and B is a member of field. So this operation plus is a field operation, not the vector space operation. This is the field operations. Field has also two operations. One is a plus and other is a dot. Okay, and this is not the same as this operations. This is the different operation, and this may be the same. It may be same, but there is not always this that case. It will be same. It can be different. Okay, so here we have a field operation dot. Okay, this should be keep in mind. That concept should be clear. Okay, now we will see some example of vector space. Okay, if we take R as a set of real number and N, what is Rn? Rn is a set of n tuples, and their element will be from R. Like Rn, we have an element x1 dot 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 xn, and xi is belonging to real number. I vary from 1 to n. Okay, now Rn over R. If we take field as R and V as Rn, is a vector space. Vector space. Yeah, one can check all the properties of vector space on our end. First example, if we want to take second example, uh, set of all polynomial of degree less than equal to n, where n belongs to natural number. Set of all polynomial of degree less than equal to n, and n will be in natural number, and operation will be usual addition and usual multiplication. Addition and multiplications of polynomial. What uh, how we add to polynomial and how we multiply uh, a constant to a polynomial. Okay, so this will form a vector space. One can check. Okay, so we end this lecture and we will continue in the next lecture. Okay, thank you.